Recording in progress.
All right, welcome to the next New York Combinatorics seminar. We're happy to have Alex Nowak, who's going to tell us about combinatorial designs and the Yang-Baxter equation. Take it away.
Thanks, Deepak, for the introduction. Thanks for the invitation to come share some of my work that I've been working on with Anya Zamoshka-Zienio. This is it's always fun to come to New York, and I'm glad I have an excuse to. I'm jealous that you guys get to do math in such a fun city.
It's not bad.
So yeah, let's here's just sort of an overview of where we're going to go today. So I'm going to start off talking about some algebra and combinatorics, so quasi groups, loops, and the sort of designs that arise from these. And then I'm going to get into the set theoretical Yang-Baxter equation, and then I'm going to bridge those two topics through sort of the set of solutions that got me into the Yang-Baxter equation. And then for the final part of the talk, we'll discuss some problems that Anya and I are looking at sort of down the line about solutions of odd order. Okay, so non-associative groups, quasi groups. So a quasi group is a non-associative group in the sense that they are binary operations whose multiplication tables are Latin squares. Okay, so another way of characterizing this is that the left and right multiplication maps with respect to your multiplication are invertible. So you're going to see these L and R maps a lot throughout the talk. So when you see L sub A and then a superscript operation, what that means is you are acting on the left by multiplication by A, and then when you see R subscript, you're acting on the right by multiplication by A. So yeah, when you've got a binary operation such that those two are invertible, then you've got a quasi group. And a loop is a quasi group with identity. So all right, so onto the designs. Steiner triple systems, these are, I mean, if you know anything about designs, you probably know something about Steiner triple systems. They're the sort of most famous class of designs. And they are defined on a point set. So Q is a point set, and then script B is a set of blocks, and these are 3-element subsets of your point set. And they have the property that every two distinct elements appear uniquely in a block, or appear in exactly one block together. So these come from quasi groups because we can define a multiplication where it's basically the incidence in the block set. So if you want to define the product of two elements X and Y, yeah, is there some feedback? Yeah, okay, there we go. Thanks. All right. Thank you. So if you want to define the product of two elements X and Y, you simply look at the third element in the block that they belong to together, and that's your product. Okay, so if this is going to be well defined, then there's got to be a lot of symmetry conditions this multiplication has to obey, and these are all of them, right? We just declare the product of an element with itself to be X. This operation had better be commutative since sets aren't ordered, right? X times Y had better be the same thing as Y times X. And then this condition here, when we multiply Y by X times Y, we had better get back to X. So that's what this identity is saying. So when you've got a multiplication that satisfies these three identities, you can build a Steiner triple system from that. And from any Steiner triple system, you can build a multiplication satisfying these identities. So
you said operations take two elements and take the unique block they're in?
no, the third element in the block that they're in.
Oh, no, third element of the block. Okay.
Yeah.
Okay.
And then here are all these symmetry conditions expressed via the multiplication maps. It says that the left and right multiplications are actually involutions and they all coincide with one another. Okay, so here's the second biggest or here's sort of there's in the succession of sort of non-trivial Steiner triple systems. The first one that you see is the phanoplane, and then the next one is this one, the affine geometry or the affine plane over the field with 3 elements. So here's a picture of that design. And if you want to represent the quasi-group operation, there's a nice linear representation of the quasi-group multiplication over the field with 3 elements. You just take Z3 squared, and the third element in any block is the sum of X and Y, and then negate that sum. In other words, points lie in the same block if they're on a line over Z3 in the plane. Okay, so that's Steiner triple systems. Now we're going to specialize this a little bit. So Hall triple systems. So Marshall Hall investigated a special class of Steiner triple systems. He considered the class of Steiner triple systems where each 3 non-collinear points will generate that design that I just had a picture of on the previous slide. So this design over here, if any triangle, so 3 points that don't lie in a line together, if they generate this, then you've got one of these Hall triple systems. That's not the characterization that he sort of initially, wrong direction. The characterization he arrived at when he was studying these things is that for every point in the point set, there is a unique involutory automorphism. And it turns out that involutory automorphism is the multiplication by A in the quasi.
So what's AG23?
Oh, that's the design that I just had a picture of.
Previous board.
Yeah.
Yeah, that one particular thing.
Yeah. So if you pick 3 elements, as long as they don't line a block together, they're going to generate that design. That's what characterizes these things. So the definition of a Steiner triple system demands that these left and right multiplication maps are involutions. But what's special about the Hall triple systems is that they are automorphisms of the quasi-group operation. So that's, for people who aren't used to non-associative algebra, that's one of the sort of stranger things to that's one of the strangest things you encounter, is this idea that the left multiplication will be an automorphism of itself. It's what's called the self-distributive property. And we're going to talk about how that self-distributive property is a big player in the set theoretical Yang-Baxter equation. Okay. So you might ask, if these Hall triple systems have this nice property of generating an affine plane, is there some sort of affine representation for them? I'm not even going to bother going into that point. Okay, is there an affine representation for these Hall triple systems? And the answer is kind of. So with any one of these Hall triple systems, you don't quite get, addition over Z3 or, collinearity over Z3 as your sort of linear representation. You get a representation over what's called a commutative Moufang loop of exponent 3. And these are very close to being elementary abelian 3 groups. They're just slightly non-associative. So these are the laws that characterize these things that these Hall triple systems are linear over. The operation is commutative, so that's like an abelian group. Any single element is going to generate Z3, but 3 elements don't quite associate. They've got this sort of weird law where you can kind of get associativity if you've got 2 copies of X, basically. But any 2 elements, if you take 2 elements, they will associate with one another. So these things basically, for all sort of small examples up to a very large order, these things are basically just elementary abelian 3 groups with an addition that's sort of twisted around by a cocycle. So you can think of them as twisted elementary abelian 3 groups. And a consequence of this is that this representation over these CML3s, consequence of this is that any Hall triple system has order power of 3. Because there still is enough structure here, even though we don't have associativity, there's still enough structure here to get Lagrange and Cauchy theorems. So the fact that every element generates a cyclic subgroup of order 3 basically like restricts the order to this. Okay. So those are the designs so this is sort of where I entered the Yang-Baxter equation. This was sort of all the stuff I studied in my dissertation. This was my background coming into this Yang-Baxter equation. So let's talk about the Yang-Baxter equation. Okay, so I'm not going to pretend I know the physics behind all this, but here it is just as a pure problem in sort of linear algebra. If you're looking for an endomorphism of V tensor V such that this equation is satisfied. Okay, so what this equation signifies is Rij is R acting on the I and jth tensor factors, and then the other one is fixed. So R12 acts by R on V tensor V here and then fixes that factor. And then R13 acts by R over here and fixes the middle factor and so on and so forth. So if these things, if these sort of copies of R cooperate in this way, we say that we have a solution to the Yang-Baxter. Okay. So this is where braids and knots come into all of this. So throughout the talk, I'm going to let tau, when you see a tau, I'm talking about this flip map where you just flip tensor factors, or if we're talking about sets, it's just going to flip the coordinates in a Cartesian product of two sets. So that's what tau is doing. So if you compose a solution to this first equation with tau, right? So if we define this new operator R hat by tau composed with R, we then get a solution of the braid equation. Okay. So this is saying that if we act by R in the first two slots, and fix the third, act by R in the second two slots, fix the first, come back and hit the first two. That's the same thing as acting by R in the second two while fixing the first, hitting the first two while fixing the third, and then coming back. So, okay, so what does this have to do with braids? Well, here's a little diagram sort of illustrating how this represents a braid symmetry. So when you're asking when are two braids equivalent, these two braids are equivalent, and that turns out to be really the only, or one of three, but this is really the significant one. This is one of the three moves that you use to ensure that two braids are equivalent. And so this equation encodes that symmetry of sort of nudging a braid into an equivalent braid. This diagram actually is more of a representation of this first one. I was going to draw a braid diagram illustrating this first one up on the blackboard, which I can get to at the end if people are still wondering about that, but I didn't quite have time to get that up on the blackboard. So anyway, these give representations of the braid group on n strands. Actually, yeah, so I'm going to turn and show the blackboard here, or yeah. So that second panel, so that's the presentation of the braid group. That's the standard Artin presentation of the braid group. And then you see the correspondence there, R hat I plus 1 gets sent to BI, and that's how you get a representation of the braid group from one of these solutions. Because the satisfying the braid relations you see up there in the presentation of the braid group. Okay. So that's the game. Find
like this R hat 1, 2 equal one another once. Is R hat 1, 2 equal, say R2, 3 or something like that?
Do they ever?
Yes, one of those just equal to another one, like is the hat of 1, 2 simply equal to some combination in general?
Oh, so like. So when would, yeah, that would, I mean, I think that would just be a different nonlinear equation, like asking when does R12 equal R23, something like that, like.
Well, yeah, and I would have said, oh, it is R hat of 1, 2 just always equal R2, 3? I guess not, because of that switching. It's not.
Yeah, so and sort of the trivial solution, you always want to, tau is actually sort of the trivial solution to this equation. So you want to think of these are like, yeah, so you want to think of these as like flipping the two tensor factors around, and then they like do other things when they're non-trivial, but it's some sort of flipping, and yeah. Okay, so that's a big problem to try and solve that equation. So Drinfeld proposed a simplification. He said just make it a combinatorial problem, make it a problem of set theory. Look for maps from a set q squared to q squared that will fulfill those relations. So if you want to, like, what does that have to do with the original problem? Basically, this would be solutions to this set theoretical Yang-Baxter equation would be all the solutions to the linear one that leave the basis fixed. You can imagine if you have one of these, treat Q as a basis for a vector space, and then sort of induce the linear operator from that, and it's just leaving the basis fixed because we're going from Q squared to Q squared. So this would be sort of like giving us sort of a special class of Yang-Baxter solutions. And the solutions that get the most attention are involutive ones. Those seem to be the ones that the physicists care about, and they seem to be the simplest to study from a lot of problems get translated nicely into group theory when you restrict your focus to these involutive solutions. So another like class, another sort of like popular class of solutions, if you kind of get your head around what this would look like, would be if you just take two permutations of the set Q that commute with one another, this would give you a solution. So this is like, so you're flipping and then you're just acting on them by those two permutations of the set Q.
So for example, R1, 2 takes the built from E3 to E.
Yes, those are.
So it takes the first two, actually the first two things, then leave the third one.
Yes, yeah, exactly. Yeah.
Yeah. You say R squared equals that. What R is?
This is the map R that's acting on Q squared.
Right.
Yeah.
Right.
Okay. So and so there's a lot of quasi-group theory that gets wrapped up in these set theoretical solutions. Oh, and yeah, here's just a note. Another reason that these involutive solutions are of such great interest is that when you make the braid group representation that you get out of this just turns into a representation of the symmetric group. And then here again, reiterating R equals tau is the trivial solution. And that's an example of an involutive solution. Okay, so I'm gonna start denoting these solutions with a binary operation notation, because I'm interested in quasi-groups and loops. So I'm interested in binary operations with certain properties. So let's think of R as, acting as two binary operations in the coordinates. Okay. So it turns out that if that white dot operation is a left quasi-group, meaning that just the left multiplication maps are invertible, not necessarily the right. If you get that, then you can associate with any of these solutions what's called a derived solution. So you build this special triangle operation out of white dot and black dot, and that's called the derived rack of the solution. So this kind of simplifies the original, right? The original solution maybe had two binary operations involved in it, but this derived process turns it into one where you've just got a binary operation on the left, and then all that's going on in the second coordinate is you're just moving x over, you're just twisting x over. Okay, so it turns out that a lot of this preserves a lot of the structure of the original solution. Okay, so this is just sort of a trick that you can use to sort of, if you're studying a particular class of solutions, the first thing you'd want to ask is, well, what do the derived solutions of that class look like? Because these are sort of yet even simpler. Okay. So so these are all just, so this is just a tool in the toolkit for people that study these things that will come up for us. Okay, and we call an operation like this, we call that a rack. It's a left quasi group in which each left multiplication is an automorphism of the binary operation itself. Remember, this is a property that multiplication in Hall triple systems, this is a property that Hall triple systems have. So those Hall triple systems were racks. Oops, I didn't get to go forward yet. Yeah. Okay, so this is going to sort of be the bridge. This derived rack is going to sort of be the bridge from the design theory to the Yang-Baxter equation. Okay. All right, so here's where I got interested in this set theoretical Yang-Baxter equation. This was the class of solutions that I stumbled upon. I was reading a paper by my former dissertation advisor, Jonathan Smith, and in it he mentions this class of solutions. He just sort of gives it as an example of kind of something else he was talking about. But so I thought, oh, okay, that's interesting. And this box plus operation, remember, that's my sort of standard notation for a commutative Moufang loop of exponent 3. So this is one of those twisted around elementary abelian 3 groups. If you like, whenever you see this box, you can also just think of addition over Z3 to the n. Like that's an associative example of these things. Okay, so yeah, there's the solution. If you have a commutative Moufang loop of exponent 3, send x, y to, in the first slot, negative, so that's the negative with respect to this box operation plus y, and then in the second slot, just send over the negative of x. Okay. That seems good. Now, the derived solution of this, as you might have guessed from the last slide, is that Hall triple system operation. Okay, so a Hall triple system shows up as the derived rack of one of these solutions. So you can build one of these Steiner triple systems with this special automorphism property out of any one of these solutions here. Okay, so that's interesting. So I started playing around with these solutions. And I was asking, okay, what properties do they have? The first question I asked is, are they involutive? Because those are the ones that everyone cares about, but they're not involutive. However, they have order 3. Okay, so that's interesting. And there is an involution that you can get out of them, but it's not R, it's tau composed with R. Now remember, there were 2 versions of the Yang-Baxter equation. One was the Braid equation, and the other was this original formulation. This tau would be a solution to the original formulation of the Yang-Baxter equation. So that is an involution in one of these solutions coming from a commutative Moufang loop of exponent 3. And when I asked, like, I remember asking sort of guy who studies Hopf algebras, and so is very familiar with the Yang-Baxter equation and sort of all its forms, what the significance of this would be, that having an involutory solution to the other version of the Yang-Baxter equation. He seemed kind of at a loss to explain what the significance of that would be. So maybe they don't care, but it turns out that you get some nice design theory out of a solution that fulfills this equation. Okay, so those are 2 properties. And then a third property that is fulfilled by these examples is their Latin. Okay, so what Latin means is that the white dot operation, so this operation over here in the left-hand slot, that's a quasi-group. It's not just a left quasi-group, it's a proper quasi-group operation. So in other words, the left and right multiplication maps with respect to the dot are invertible. Okay. So those three properties is where we sort of went from. So we started asking, what do solutions to the Yang-Baxter equation that have these three properties look like? Order three, compose them with the flip map and you get an involution and they're Latin. So that was the class of solutions we wanted to study. The term we settled on for such a class of solutions is braided triality set. So the word triality coming from S3, and it's because one of these solutions and tau together, they give a they satisfy the relations in a presentation for S3. So we went with braided triality set. So braided as in they, they satisfy the Yang-Baxter equation. And then triality, as in they play nicely with the tau map to give us a S3 relations. So we call them braided triality set. So we asked the question, how much can a Latin braided triality set? So this is an acronym you'll see throughout, LBTS. How much can that differ from rho and rho prime? So rho and rho prime are what I'm using for those original two examples that I stumbled upon in that paper. Okay, so how unique are these two solutions in having those properties of having order three, giving an involution when you compose with tau, and being Latin? And the answer is not that much. It's actually pretty unique to these maps, or it's that any solution that has these properties is going to be built from a rho and a rho prime in a very specific way. And so this is precisely how we articulate that. So if you've got one of these solutions, again, order three, when you compose with tau, you get an involution, and being Latin, you can split it up. So no matter what this solution is, you can split it up into a commutative Moufang loop sum of two sort of sub-solutions, such that when you restrict R to the substructure on the left, that has the form of one of those rho solutions. And when you restrict R to that factor on the right, it has the form of one of those rho prime solutions. So these essentially just, they all come from Hall triple systems and commutative Moufang loops in a certain sense. We can factorize any of these solutions into a sum of two such solutions.
Do you get any kind of converse now? Like if you have those kind of solutions, you get back to
yes, yeah. So if you took a sum of two such solutions, yes, they would have order three, they would have they would have those triality properties. Yeah. Okay, so how do we get there? The path to that decomposition theorem. So the first big hurdle that we cleared was proving that we actually only have to worry about one. So kind of like derived operations, those derived Dirac solutions, we really only need to worry about one binary operation. So it turns out that they all have this form where we've got a white dot operation on the left, and then what goes on the right side of the image can be expressed in terms of the white dot operation. So x to the s, that's going to be my shorthand for the image of x. It's kind of a mouthful. The image of x under the inverse of left multiplication by x. Okay. So you can think of it as x divided by itself in a certain sense. In a group, this would be trivial, right? This would just always give you the identity. This is dividing x on the left by itself. So in a group, that's always just the identity of the group. But in quasi-groups, that doesn't happen, right? There is not necessarily the presence of an identity or anything like that. So this can be a non-trivial map in general quasi-groups. Okay, so the proof is not hard. It's just tedious. We based it on, we plugged this into prover 9. We asked prover 9, what does black dot look like? And it turns out it's this. And so it was sort of a feat of human computer interaction to translate prover 9's output into into, yeah.
What's prove or not?
It's
Plan matter space, it's after the first
Oh.
plan's failed.
Yeah.
I don't know, no.
Yeah, it's a automated reasoning software.
Oh.
Yeah. Yeah, and it's well designed for universal algebra for, putting identities in and asking it to prove new identities from those. It's very good at that.
Cool.
Okay. But once you have this, that everything flows through the white dot operation, then you get this correspondence between these solutions in Hall triple systems, right? So the derived rack, you can prove that the derived rack of any one of these LBTS solutions is going to be a Hall triple system. And then conversely, if you start with a Hall triple system, you can build an LBTS as such. And these constructions are mutually inverse. So, right, if you start with a LBTS, build the Hall triple system and come back through that, you're going to land back with the original LBTS that you started with. Okay. And so how does this help us get to that sort of decomposition theorem? Well, so if we fix an LBTS and we say, okay, if we've got an associated Hall triple system, that means we've got an associated commutative Moufang loop. That means we can fix an identity. That means that there is an identity with respect to that commutative Moufang loop. So let's call, it turns out that QE structure is the kernel, so to speak, of this map square dot. So what square dot is, it just sends x to x times x under the white dot operation. And this isn't quite a kernel because it's not always necessarily a homomorphism of the structure, but think of it as a kernel. So what characterizes this set is that it's all the points in your original solution that are negated under S. And then when you look at the image of that squaring map, that turns out to be all the points that are fixed by S. So for any x and q, you can actually represent it as a sum of two elements, x, I'm denoting x sub -1 and x sub 1. And this x sub -1 comes from QE and this x sub 1 comes from P. So x -1, so every element can be represented as the sum of an element that's negated by S and the sum and an element that is fixed by S. Okay, so negated by S, that's one of those row type solutions. Fixed by S, that's one of those row prime type solutions. So you can just directly factorize any element into two elements that sort of act as if they are one of those original solutions that inspired this whole thing. Okay. So the sort of, after stepping back and thinking about what we had just done, we're asking why, because this is like, how strict were these conditions, or just how, like, why did we get such a sort of rigid structure by assuming these things? Because typically you can't, like, I didn't include a slide on this, but this allowed us to solve the quote unquote isomorphism problem for these solutions that have these three properties. That's typically not something that you do in Yang-Baxter with Yang-Baxter equations. That's typically that's just typically a question that's beyond sort of most classes of solutions that people look at. They're not trying to classify them up to isomorphism. They're doing other things with them. So I guess the question is, did we ask too much of these things? So if you take away, so here's some answers. If you take away 3, so if you take away the Latin property, then then this is a big problem. Then you lose this black dot being characterized in terms of white dot. So then that would, once you take away 3 and you have these two conditions, then you're more in a world that you're used to with Yang-Baxter equations, where you're not going to be able to classify them up to isomorphism. You're just gonna look at, say, what are called their structure groups and see if you can say anything interesting about their structure groups. If you take away 1, so take away the order 3 and just leave these two conditions, you actually still have the black dot is in terms of the white dot. But the reason I didn't talk about that today at all is because you lose all the sort of combinatorial design theory when you take that condition away. And commutative Moufang loops are replaced with a more esoteric class of loops. So the paper that this is based on, that is actually the majority of that paper, is looking at solutions that just satisfy these first two conditions. And you can still solve the isomorphism, or wait, no, sorry, second two, I meant to say. These solutions that just satisfy these second two conditions. You can still solve the isomorphism problem for those solutions. Now that really contrasts with involutive Latin solutions, right? Even if you just take the traditional involutive solutions that people are interested in, even if you look at the Latin ones, that the isomorphism problem in that class is still very, very hard to solve. So there's something about R composed with tau being an involution, that being an involutory solution, quote unquote, that really sort of narrows the possibilities of solutions. So then if we just look at solutions that have order 3, that condition by itself is surprisingly very restrictive, which again is very different from looking at solutions of order 2. People have spent many years trying to sort of get a hold on solutions of order 2, and solutions of order 3 are sort of much more restrictive in the following sense. They can only exist at certain orders. There's a very sort of narrow class, it's a very narrow class of integers at which these solutions of order 3 can exist. Okay, now I'm bringing this up because this leads to another class of combinatorial designs. Oh, and here's just a contrast with involutive solutions. They exist on any set of any size over 2, whereas these ones of order 3, you've got a restriction. Or for that matter, solutions of order 2k will exist. They'll certainly exist on any set of size greater than or equal to 2k. So even solutions are plentiful, even order solutions are plentiful. Odd order solutions seem to be less plentiful. So over there on the blackboard, those permutation type solutions, that's how you can sort of construct a lot of even order solutions. Okay. So the reason that these order 3 solutions, the possible sizes on which they can exist are so restricted has to do with another class of combinatorial designs. It has to do with what are called Mendelssohn triple systems. And these are basically just a non-commutative generalization of Steiner triple systems. So you take a Steiner triple system, and rather than the blocks being sets, they are cyclically ordered. So like this block would be the same as this block, would be the same as this block. And you end up with an operation that obeys this identity, this semi-symmetry identity that all Steiner triple systems do. And you get idempotence, but you don't have that commutative identity that Steiner triple systems have. And they have the property that each ordered pair appears exactly in one block. Whereas Steiner triple systems, it was each 2 elements appear uniquely in a block. Here it's each ordered pair appears exactly in one block. So X followed by Y might appear in a different block than Y followed by X. So that's why we lose commutativity when we build these designs. Okay, so and then the restriction on the size of order 3 solutions comes from the fact that you can show that the derived rack of an order 3 solution is a Mendelssohn triple system that's also a rack. And these rack MTS have to come from modules over the Eisenstein integers. And that's a whole nother story. But it turns out that that module structure restricts the size of possible sets on which these things can exist to that to this set right here, integers of this form. These also happen to be the possible orders for modules over the Eisenstein integers. So even order solutions, so the main story I'm trying to tell here is even order solutions are plentiful, odd order solutions not so much, and that seems to be restricted by designs that are inherent to the solutions. So what about higher order? So we've been sort of looking at order 5 solutions, and it seems that the racks associated with these order 5 solutions have to be what are called Mendelssohn 5 designs. So you've got blocks of size 5, but the existence spectrum is even more restrictive. So doing a computer search up to order 62, we found solutions of order 5 only existing at these orders: 1, 5, 11, 16, 25, 31, 41, 55, 61. But there are plenty of Mendelssohn 5 designs coming from racks that exist at orders other than these. So there's something funny that we're getting an even more restrictive class of designs that are sort of controlling solutions of order 5. And we're trying to figure that out right now. Yeah. And that's the point I just made. There are rack Mendelssohn 5 designs and many more orders than this. Okay, and yeah, there's the pictures that I had came from these sources, and thank you for your attention.
Thank you. Any questions?
Oh, I can clap, right?
Right, we already clapped once.
Right.
Any questions in person?
Guess you don't know if any, you said you didn't really know the background. If there's any, what was the rationale for the Yang-Baxter?
So in particle physics or in statistical mechanics, when you've got an integrable system modeling gases or like that system can be described. It's so-called scattering matrix is going to be one of these solutions. Those are the words that I know.
Okay. So it's so hard to solve. Like, let's look at this simpler, but still very hard question.
Yeah,
Okay.
yeah.
Other questions in person?
You mentioned that this instead of involutive, right, solution that you have a sort of degree, and you said like there was no rationale from physical perspective.
Right. Yeah.
Could it be that this equation could have a different interpretation rather than coming from that physical model, or like people looking into this equation that could represent a different phenomenon?
Yeah, the other class of solutions that people have started looking at is idempotent ones. So solutions with R squared equals R. So that apparently solutions like that are related. You can use these to say things about semigroups apparently. And but I don't know the story there. But so yeah, it turns out that just pure semigroup theory has some interest in solutions that satisfy this relation. Yeah. That's the only example I can think of off the top of my head.
In the prover 9 thing.
Yeah.
Does it basically prove equation type results, or does it prove more general mathematical quantity?
Yeah, you can I mean, yeah, you can formulate just propositions. But yeah, I basically I've only used it to do equational reasoning.
And do you give it the result you want, or do you have it say find the result?
Yeah, you say like, well, so it comes with it comes with another software called Mace 4. And so and that's a counterexample seeker. So you say, assume this, here's what I want you to prove. And so it'll simultaneously try to prove that identity from the axioms and look for a counterexample. It's very handy. Yeah.
Any questions on Zoom? I don't see anything. All right, in that case, let's thank the speaker again. Thank you. All right, see you all later.